Hello and welcome to my video, lesson 6.4 on the wave mechanical model. So essentially, de Broglie figured that if electrons can act like waves using the de Broglie wavelength, then not only, we can't say that electrons are in a specific location, we can't say they're necessarily orbiting the nucleus with a location known, we kind of just say they're in a cloud. And because of this, we talk about Schrodinger's uncertainty, or Schrodinger's cat situation, or we talk about Heisenberg's uncertainty principle. That is slightly beyond physics 30, but it's interesting to know about and good to know about for the future. But essentially it means either we know the speed or we know the position of the particle, but we can't know both. The only way to determine the location is to alter the momentum, alter the speed, right? So we have to stop it or hit it with something. It's like being able to measure the position of a tennis ball in a room, but you're blind. So the only way to measure the tennis ball is by throwing another tennis ball and listening to see if it hits the original tennis ball. But the moment that you've hit it, it now has a different momentum than it had before. You can listen and tell where it is or where it was, but you no longer know its momentum. But if you don't throw that ball, you can talk about how fast it's going, but you don't know where it is. And so this is the Heisenberg uncertainty principle. It's kind of confusing, a little bit beyond physics 30, but it's very, very interesting, and I highly recommend watching some other videos like Veritasium to get a better idea of what that looks like. But essentially, all you need to know about is that if this is true for electrons, it's actually true for everything. It's true for alpha particles, protons, like helium, or just protons by themselves, or positrons, or whatever you have. But you can actually do a de Broglie wavelength calculation on anything, including me. So we're going to do that with these two examples. Pause the video here, try them out, and see if you get the same answer as I do. Alright, so what we're going to do is find the wavelength of me. So what we're going to do is just notice that I'm going to have momentum. So momentum equals momentum no matter what. And so it's h over lambda. So we're looking for the wavelength, so it's going to be lambda equals h over mv. And so you can now solve for my wavelength, which will be 6.63 times 10 to the exponent negative 34 times my mass at the bottom, or divided by my mass, which is 70 kilograms, times by my velocity, which is 30.6. And you can see that because those values are pretty big, it's unfortunately not so good. 3.09 times 10 to the negative 37 meters. So it's really, really small. Basically non-existent, right? So you can't measure the wavelength when it's this small. Alright, so what is the de Broglie wavelength of the baseball? Well, it's going to be the same process as before. We're just going to do mv equals h over lambda. Then we're going to rearrange that, so it's lambda equals h over mv. And then we can go ahead and plug that into a calculator. So basically the same as last question, except that our mass is going to be much smaller. The smaller the mass, the more easily it can be affected. But because it's also traveling slightly faster, it's not going to have a very significant difference compared to me. So my de Broglie wavelength and the baseball's de Broglie wavelength, you'll find is very similar. So I hope this video helps you better understand the idea that all matter can be waves, and yet it's also kind of particle at the same time. And so those electrons are in this cloud around the nucleus, and that's all based off of this de Broglie wavelength idea. I hope this video helped you better understand the wave mechanical model, and good luck.